Okay, hello everyone joining online. As indicated, we are due to start at 11 CET, so we have a couple of minutes. We have to wait because we have a very large number of participants, more than 300 joining online. So in the meantime, please, Firat, would you be so kind as to project the videos, the promotional video of the sponsoring company of the webinar, please?
CFC is an independent consulting engineering company whose expertise covers any kind of projects involving special structures, from long-span and signature bridges to high-rise buildings, large domes, transportation stations, and industrial constructions. Established in 1964 by Professor Carlos Fernandez Casado and his two young disciples, Javier Mantarola Armisen and Leonardo Fernandez Troiano, the firm has decisively contributed to the development of the structural engineering with many innovative and record-breaking works. CFC has retained, since its origins, the founder's philosophy of trying to find the most strict and efficient structure for every problem, considering the aesthetical, environmental, and cultural facets essential input of this exercise. Continuous innovation and cutting-edge technology are the hallmarks of the firm. CFC services comprise every stage of the design process, from conceptual and feasibility studies, passing through detailed design and value engineering to construction support and project supervision. Services also cover independent checking and forensic engineering. To this end, it has a large team of highly specialized professionals trained in the study of complex structural problems. Bridge professors, university professors, national engineering awards, academicians of the Royal Academy of Fine Arts of San Fernando, and members of technical committees at national and international level who have been recognized with a multitude of awards as well as their projects. CFC works can be found in more than 30 countries worldwide. Its international activity is supported with the help of local branches and strategic partners in 15 countries of Europe, South America, North America, and Asia. The company is used to the multidisciplinary and cooperative work required by an increasingly globalized world, having large experience of collaboration with other international engineering firms, major construction companies, local administrations of many companies, and academic and research institutions. CFC. More than 50 years designing structures of the future.
Okay, welcome to everyone. I propose to make a start. So good morning to you all. I would like to welcome you this morning webinar, which is organized by the Spanish group of IABSE. The title of the webinar today is the Cebu-Cordova Cable Stay Bridge, an example of innovation and resilience from concept to completion. And let me tell you something outstanding about this project in case you don't know it. It has been awarded at the 2023 IABSE Project and Technology Awards twice as winner in the category Innovation in Construction and shortlisted in the category Large Road and Rail Bridges. So congratulations to all the people, institutions, and companies involved in it, representing most of them by the panelists present today. This webinar will be recorded as for previous webinars. All of the recordings are available on the e-learning webpage that I think Brenda is going to post into the chat, the link to the webpage for you. At the end of the webinar today, we'll have a 10-15 minutes for Q&A, and I will conduct it by the Q&A chat function in Zoom, you can see. We'd like to announce that we have more than 300 registered attendees for the webinar today, so it's a grand number. We are very happy for that. And we look for your active participation in the webinar today. My name is Dolores Pulido. I'm the chair of the Spanish group of IABSE, and I have the pleasure to act as your moderator for this webinar. I'd like to introduce the 9 speakers you can see on the screen. Daniel Muñoz, Acciona Construcción, brings over 20 years of expertise in designing and constructing large-scale infrastructure projects across various countries. In the Cebu-Cordova project, he held position as the head of engineering and then project director. Currently, he serves as the head of the Road and Bridge Special Business Unit at Acciona Construcción. Julio Ruiz Cabrero, Acciona Construcción, has more than 25 years of experience in major bridge construction in Europe and the USA. In the Cebu-Cordova project, he played crucial roles, including selecting the optimal construction procedure during the tender stage and serving as the project director in the first 2 years. Currently, he holds the position of Country Construction Operations Director at Acciona Southeast Asia. Laura Granda, Acciona Construcción, possesses a strong background in design engineering and extensive construction experience gained over 24 years. Her notable contribution include her role as the design manager for the Cebu-Cordova project and her involvement in the design of temporary works for the main bridge. Antonio Jané Olivan, Acciona Construcción, has extensive international experience in bridge construction, including his role as the Cebu-Cordova main bridge construction manager. He's currently involved in the construction of precast segmental viaducts for the Malocos-Clark Railway Project North-South Commuter Railway Package 2. Javier Muñoz Rojas, Carlos Fernández Casado, Main Bridge Design Project Director. José Manuel Domínguez, Carlos Fernández Casado, Main Bridge Design from Office Manager. Pedram Manocheri, Carlos Fernández Casado, Main Bridge Special Study. And Robert Athwatt from COWI, graduated in 1974 and worked in construction until he joined COWI in 1997 to work on foreign projects. Since then, he has been project manager of 8 projects, culminating in Cebu-Cordova Link Express in Philippines, where he joined the project in November 2016 and remained there as owner engineer until completion in 2022. He has therefore been involved through the project from the tender phase. We have panelists, as you can see, located in many parts of the world. In Philippines, Julio Ruiz Cabrero and Antonio Jané Olivan, UK, Robert, and the rest of the panelists in Spain. So I'm delighted to start the webinar and very focused on this project. So I'm going to hand over to Julio Ruiz Cabrero to give his presentation. So Julio, it's over you, and please, each speaker at the end of her presentation, please give the floor to the next speaker. So Julio, the floor is yours.
Okay, Javier, sir. You share the presentation, Javier?
It's working.
Okay, next slide. Yeah. Next slide, Javier. Okay, good morning and good afternoon here from the Philippines. Thanks for allowing me to make this small introduction to the team and place in context our stay cable bridge from CCLEC. The project, as you can see in the image, has been built in the island of Cebu. The bridge itself connects the island of Cebu and the island of Mactan, where the International Airport of Cebu is located. Prior to the construction of the CCLEC project, there were 2 existing bridges. One is the Mandaue-Mactan Bridge, built in 1972, and the other one is the Marcelo Fernand Bridge, built in 1991. They are 1.4 kilometers apart. The new CCLEC project, and with the stay cable bridge, is built 7.5 kilometers south from the city. The main targets of this new construction was to decongest the traffic on the existing bridges and make a better connectivity to the international airport, but also development of the south of the Cebu city and the municipality of Cordova. Next slide, please. Yeah, here you can see the team that have made this project possible. First, the employer with CCLEC. CCLEC is a Metro Pacific Toll Corporation company that, together with the grantors, Cebu City and Cordova Municipality, are the employer, our first team member. Then after that, we have COWI and DCCD Engineering Corporation as a consultant that were engaged in August 28, 2016 as technical advisor and owner's engineer. Also in the team was engaged Norconsult as independent consultant for the grantors. And last but not least is the design and build contractor with this Cebu joint venture made by Acciona, who is the leader partner with the majority of the shares, with the Spanish base, and then our local partners with our First Balfour and DMCI. Within our design and build joint venture, we have as main designers Sener and Carlos Fernandez Casado, who is the main lead on the main span bridge on the stay cable bridge that is part of this presentation. The notice of award was given in November 2017. The contract was signed in December 2017, and then notice to proceed was 2018. The bridge was completed in April 2022. Next slide. As our main topic, as I mentioned earlier, is the stay cable bridge. Here you can see some of the points that the team is going to develop and is going to detail during the webinar. The concept design, how we reach the design that we have today, the detailed design challenges that we have been encountering during the detailed design process, methods of construction, the innovation and improvements that were done from the tender to the final design, and of course also the external challenges that we have faced in the last years, like COVID and one of the biggest typhoons that the Cebu Island have received recently. We believe that the team we have achieved a good level of innovation and performance at all levels, not only on the design, but also in construction. And the collaborative approach that has been running through the project is a good signal for the future. Here you can see in the picture below some of the areas in construction where some innovation improvements have been developed during the construction, and the team will explain those later. Next slide. That have been translated, among other awards that the project have already received, in the IABSE Project and Technology Awards in 2023. The project won the Innovation and Construction Award and was finalist in the major bridges. The project has been consistent along the life in the construction methods, from the tender to the final completion, which generally is a good idea and a good signal, and we believe is part of our success in the journey. And without more delay, I'll give the floor to Robert for starting to explain the details. Robert.
Good morning, everyone. My name is Robert Uthwatt, and I will be briefly describing the contract with respect to its shape, the iconic features, the innovative technologies, and the tendering process. COVI DCCD was brought into the project in August 2016. That was after the initial design had been completed. COVI is based in Denmark, and DCCD is one of the largest consultants in the Philippines. I moved to Manila in 2016, from where I was involved in putting together all the contract documents as well as overseeing the tender of the project. And then from January 2018, moved to Cebu. I was in charge of the supervision and construction. I had a team of 2 permanent staff from COVI and 23 from DCCD. You can see our picture there. Next slide, please. Okay, the original concept for the main bridge was an arch bridge. You can see in the picture there. The client, however, which was Metro Pacific, wanted a slimmer design for the main bridge and engaged COVI DCCD to create an alternative. The initial scheme put forward by ourselves was a single pylon stay cable bridge, but this was not accepted by Cebu Coast Guards or the CPA, especially after a collision with a survey barge happened at the same time that we were having a meeting to discuss this in Cebu. We had suggested this as it allowed the stay cable bridge to be straight with the road curvature accommodated in the next section. There are a number of reasons why it was advantageous to replace the original concept of an arch bridge with a stay cable bridge. These can be split into the following categories, 3 categories: aesthetics, constructability, and durability and maintenance. This new bridge was scheduled to be completed just before the celebration of the 500-year anniversary of Magellan's landing in Cebu, and provided a unique opportunity to present an iconic structure which celebrated this anniversary. As far as constructability is concerned, in the original concept of the arch bridge, the method of construction was not fully explored. The weight of the bridge is approximately 8,300 tons, and location in an important shipping channel would seriously hinder the movement of ships during construction. Maintenance and durability. An arch bridge is a complicated steel structure which needs monitoring for rust in this environment after only a few years' service. And then once the initial period is over, there will be constant painting required. The design of the stay cable bridge complies with AASHTO standards, even though the contractual service life for this bridge is only 50 years. However, it can be expected to actually last quite a lot longer. Next one, please. Right, the second option that we put forward was the 2-pylon stay cable bridge, which was actually the one accepted by all parties. This was more complicated as the road curvature started within this stay cable bridge. The original design included the Guadalupe ramp, which connected to the central part of Cebu. And I'll actually mention this later. Next one. Aesthetics is very important aspect of stay cable bridges, and COVID DCCD utilized the services of the architects Deasing and Weitling to produce an appropriate iconic structure. The Cebuanas are very religious people, and so they considered either trying to get a cross or the praying Madonna into the picture. Next slide. This just gives you an idea of what the cross, what they look like, and the architect's sketches on the right-hand side. Next slide. And this is the idea of the praying Madonna and the shapes that we looked at that could somehow bring over this the effect. Next slide. But in the final design of the stay cable features the cross. The idea was to have this bright and defined to allow it to be seen from as much of Cebu as possible, as well as from planes landing at the nearby airport. And you can see from the pictures, we ended up with having 4 crosses in each pylon, i.e. 8 crosses in all, and lit up with in between stainless steel frames, and we got about 25,000 lights to illuminate the bridge. Next one. COVID DCCD produced a reference design. This based on the agreed main bridge layout, with most other sections in the bridge remaining as per the original design before we took over. And this was used to define the features for development of bid designs for the ECI contractors. The mandatory requirements for tendering: the main span of 390 meters, a concrete box girder with central stay plane, roadway cross section, a navigational clearance, and the architectural features of the pylon. These had to remain as is. Next one. Right, Metro Pacific, after discussions with DCD, decided to tender the project as follows. design build contract under the FIDIC conditions of contract, not to follow the traditional bill of quantities form of monthly evaluation of work, but to substitute this with a set of payment milestones. And however, tender BOQ based on COVID-DCC design was used to produce a tender cost. This would allow comparison when carrying out the tender evaluation. Okay, next one. In September 2016, Metro Pacific started the pre-qualification process with 18 interested contractors inquiring over the project, with some of them deciding to form joint ventures. Metro Pacific then requested each of the preferred 6-number JVs for a presentation in which they had to present their ideas in line with a provided format. After this process, the following joint ventures were chosen to enter the next phase of the tendering process: GS-EC FF Cruise and Acciona DMCI First Balfour. And this next phase was called the early contractors involvement. Next slide. No, sorry, let's keep it as. In September 2016, Metro Pacific, sorry, I've got it. Right. This early contractor involvement started in January 2017 and consisted of a period of 4 months in which contractor, client, and client's technical advisors and owner's engineer discussed all aspects of the contract it's very important, in a non-contractual environment. We were able to discuss methods and everything which might benefit everybody in the contract. It should be noted that discussions with each JV were kept confidential, which allowed methods and materials to be discussed openly. Tenders from the 2-number ECI JVs were submitted 23rd of May 2017, and by mid-July, COVID-DCC presented a tender report to CCLEC, which was the newly formed subsidiary to Metro Pacific. This led to discussions between all parties, and in December 2017, the contract was awarded to TLJV. The actual contract started in January 2018, with the first 7 months taken up with design, setting up offices, agreeing methods, etc. The construction commenced in July, just as we started to move into the site offices. The Guadalupe ramp, which was included at the tender stage, was removed from the contract due to problems associated with the right-of-way. Sorry. Next slide, please. Right. Innovative techniques. The ECI process and subsequent contractor brainstorming resulted in the use of a number of innovative techniques. I just list a few of them here, but there were more. Cebu's harsh reality, viz. Typhoons, storm surges, etc., and scarcity of materials resulted in an innovative and sustainable causeway transverse section design. Secondly, use of a high technology Rubica underslung form traveler to adapt to the variable deck width and curved alignment. The use of a novel clamp shaped pier head was designed to restrain the uplift of the deck at the edge back span piers. Use of PT strands as both active and passive reinforcement for anchoring intermediate piers and deck to reduce space proofing. And design and use of Acciona's launching gantry to allow construction of approach bridges with complex geometry. And one extra I'll just mention is that in fact, Acciona brought over from Spain their entire blacktop crew, including equipment and people, such to ensure that the blacktop was very well laid and smooth as it is now. Okay, thank you. I will now hand over to CFC.
Recupero la pantalla. ¿Qué? ¿Está la pantalla? Sí. Sí, creo que tienes que compartir pantalla. No estás viendo, ¿no? Hello. Just give me a second, sorry. Just to... Okay. Now we are on behalf of CFC and the team involved in this project, we are going to describe the special features of the structural design, starting by a general overview of the general features of the project and the adjustment that were introduced in the reference design. And later we will focus on the special design features of the project. One of them was the construction, as we will see later, due to the unbalanced situation of this bridge. And also we will talk later, our colleague Pedram will talk later about seismic and wind special effects in the design of this bridge. As Robert has mentioned, during the tender stage, we were involved with Acciona technical team to bid this challenging project. We started, as Robert has mentioned, with a single pylon cable stage bridge, but was quickly modified to a double pylon cable stage bridge with these arrangements, this very orthodox and good arrangement of nearly symmetrical bridge in the longitudinal elevation, but that has some problems regarding, as Robert has mentioned, the curve alignment of the road in the Cebu side that, let's say, was critical for the proposal that we later developed. The main design constraints of this bridge that we have to deal and analyze with Acciona and its team concerning the structural design was that we are logically in a region of high typhoons and the design speed reached 250 kilometers per hour. Of course, the Philippines is a very high seismicity region, and we will see later that we have to deal to up nearly 0.5 G PSA accelerations. We are crossing over a busy navigational channel, so the ship impact loads that were evaluated by COVID reached about 110 meganewton. Later, we also, concerning foundations and soil conditions, two critical topics. First, that we have very different soil conditions at both sides of the bridge. And also the soil conditions were, let's say, very different from the initial reconnaissance, and that allow for initial, in the reference design, a proposal that was proved to be very difficult to build. And of course, this is very important as well. This is not a condition from the environment, but it's a condition from the contract that the bridge was to be built very quickly. So we have to find with Acciona a high efficient system to construct it. And all these constraints are not only technical data from a standard, it's real. This is real. The region suffers seasonal winds, and the construction suffered during the last year. The bridge was nearly closed, but you can see here the Odette typhoon affected Cebu very critically. This is very close to the bridge. You can see it behind it, this building, and how it suffered the effects and what was the effect in the local villages. Earthquake is also a very critical issue and is very important, and the country has suffered repeatedly very high earthquake. This is the effects in very important church in Cebu that on a 2013 earthquake. Of course, the navigational channels, I have mentioned, is very busy. You can see the size of the ships that enter the Cebu port, that is after the bridge. So with all these constraints and with the reference design of developed by COVID, then we put the focus on, this is some of the elements where we put the focus, how we can solve or improve or simplify, let's say better, the problem with the curve girder and the connection of the rimes in the Cebu side, how we can resolve the new conditions for the foundations that were initially proposed with deep caissons and shallow foundations, how we can improve in order to reduce the construction cycles the number of cables, because as you know, cable installation is critical in this kind of bridges and it's a time-consuming operation. We also detected that wind was very critical and conditioned many structural elements like the mast of the pylon and also the depth of the girder or the girder transmitted a lot of reaction to the foundations. So we tried to optimize the depth of the girder as well. And also, finally, the back span arrangement that we will see later in order to simplify or let's say, or to make easier the construction and the stability of the unbalanced situations during construction. So what we did, and this is our proposal, as you can see here, we modify the proposal from CJV, from Acciona, modify the back span arrangement, reduce the length in order to avoid the curved part of the road. We reduce the number of cables and we increase then the spacing between them in order to speed up the construction cycle of the main span. We also reduce the depth of the girder, and this has a lot of impact later in some structural design features. We also add an additional anchor pier that helps us to balance the bridge during construction and also in the permanent situation. And of course, we also introduce some changes in the foundations, and as we see later in the connection with the approach viaducts. So here you can see the comparison between the two proposals. Of course, we retain the main requirements of the design, the architectural features that Robert has explained, including the ornamental cross, of course, the geometry of the pylon with some adjustment required for structural analysis, the concept of the cable stage bridge, and a single plane of axial central cables with a concrete boss girder. This is the comparison between the final proposal of the CJB and the initial design. We remove the transverse ribs. This was intended to simplify the formwork and the construction of the girder. That requires us to incline more the webs of the boss girder, and we also modify the internal concept of concrete diaphragm to transfer the load to the cables by a new solution based on a steel structure on a delta frame that we will see later. Due to more detail or our analysis of the structure, we also have to adjust the initial geometry of the octagonal pylon or tower. We keep this concept, but it was necessary to extend the lateral dimensions of the pylon in order to resist the transverse wind. In parallel to this increase in the dimensions, we also adjust a little the concept of the cable anchor inside the pylon, with also using a steel structure, but only connected to the ends of it, to the concrete sections. As mentioned, we have to modify the initial concept of the main pylon of the pylon's foundation from shallow foundation supported over the seabed. It was proved that were very poor conditions, and actually there were also possibility of a scour, so a more conventional piling solution was used with big diameters up to 2.5 meters in order to resist large horizontal forces. So this is the summary of what was finally designed, a bridge of what we reduced a little the total length of the cable stage bridge. We kept the 390-meter main span, of course. The width was slightly increased in order to accommodate the new dimensions of the pylon, but it was accommodated. It included 2 lanes in each direction and the pedestrian areas. The depth was slightly reduced. We also modified the segment's length, and in order to accommodate the new cable spacing, we reduced the number of cables and the other details that have been mentioned. Well, this is the final arrangement of the bridge. You can notice that compared to the reference design, our back spans are shorter, so let's say are less efficient to balance the main spans. So that's why we need to introduce new solutions to counterbalance the loads of the main spans. You can see here it's bending moments in the under permanent loads, just to show you that, of course, in the main spans we can balance perfectly the permanent loads, but due to this situation in the back spans, you see the bending loads are slightly different from what is normally seen in a cable stayed bridge. So how we balance the main spans? We used 4 solutions. First one are internal concrete counterweights inside the boss girder in the back spans. The second one is we use anchor piers, and we introduced an additional one. It is monolithic to the girder, so it was require a very complex situation that will be explained later to connect the girder to the pier with pre-stressing. And finally, we use this unusual solution for the end tie-down pier with this kind of clamp elements to block the girder. We could not use the same solutions as in the intermediate pier because we have to liberate longitudinal movement, so we could only block transverse and vertical movement in this pier. So we adapted the initial geometry of the pier designed by the architects, but by adding these external elements to use this to block it. And finally, we also extend a little the girder from the end pier, so to support the approach viaduct done by precast concrete girders supported over a half joint. It was necessary to do this transition between the girder and the new approach viaduct, but by using this solution, we take advantage of the weight of the approach girder, so to reduce the unbalanced force at the end pier. This is the final arrangement of the box girder. As we have mentioned, this is the main span. We also try to optimize the weight of it, so we reduce to the minimum the depth of, and the dimensions of the girder. As you can see, the web is very, very thin, at only 30 centimeters. This is a view of how it's, let's say, a conventional solution. And here you can see sections of the typical sections of the main and the back span. The back spans, of course, the geometry is the same, but dimensions of the lower slab and also the webs are thicker in order to resist or to receive the loads of the internal concrete that are placed in this section. The pylon of the towers, we kept, as mentioned, the concept of Kobe and its architects, but we changed slightly the dimensions, mainly in the mast, where we detected that the wind was critical for, and it was very, let's say, very strict, the dimension that initially planned, but keeping, of course, the external ornamental crosses, and the solution for the cables was, as said, similarly to the solution with a steel structure, but in this case we use these elements only connected at both edges, and we also left an open room for the access to this part of the upper mast. The girder, the cable anchor in the girder was also we also use a steel structure, this solution that has been used in many other structures. Later it will be describe some particular phases of the design, but it was done with a precast shoe here, concrete, that was already installed with the structural elements. The connection was done between the concrete at the webs and at the upper slab with shear studs. Of course, this bridge, I'm not going to talk too much about the structural analysis, but just to mention, as a part of the innovation, these complex bridges require also very complex analysis in order to optimize. In particular, in design and build competitions like this, we have to, let's say, optimize the design to the maximum in order to be the most competitive. So we use all the tools available nowadays for this powerful structural analysis software. We use the general model based on linear elements. We also use some shell elements to analyze the forces diffusion along the girder. We use, of course, many local models to analyze very critical sections like the connection of the pylon and the girder, and the transition that was done internally the girder, as you can see here, with these are solid elements, finite elements models. We also, the connection of another critical element was the connection of the delta frames, the cable anchors in the girder to the concrete, and also the design of this steel element. The steel anchor elements in the upper mats of the cables, it's also a critical element. We also analyze locally the steel structure and also the concrete behavior and how loads are transferred and affect the concrete section. It's important. Of course, the half joint, the end half joint that connects with the approach viaducts, it's a critical element as well, and it departs from, let's say, the strength of materials approaches. So we have to use this solid element to understand and to assess how is the load transfer between all the elements involved in this section. And just I mentioned, because before giving way to the rest of the team of CFC, also special effects that were critical for the design and that were involved in the previous structural models is that we have to deal with different soil conditions. So the seismic analysis had to be taken into account the spatial variability of the input in the different supports. We also carried out, during the tender stage, you apply the CFD tools in order to optimize the drag coefficient, so to reduce the wind forces. Of course, this was assessed later by the wind tunnel test, and also was very critical and will be later assessed, the soil structure interaction for the seismic and the ship impact design. So main ratios of the girder, reinforcement, main width, main concrete thickness, and as you can see here, pre-stressing ratios are very low, and also we combine temporary only used during construction with permanent pre-stressing. The cable stays, as you can see here, it's about 45 kilograms per square meter concept. So now I give way to my colleague, Jose Manuel Dominguez.
Okay, I don't know if you can hear me properly. Okay, so we're sharing the mic. Okay, so I will talk about the construction from the design aspect. Okay, so the first one is what already has been mentioned by Javier, is the uneven span length between the main span and the main span. So with this, we have two typical situations. The first one is we have a free cantilever without the stay cable that mainly are taken by the upper slash PT cables. Okay, there is also another situation, in the ones that we reach the first stay cable, we encounter the situation that two segments in the main span has to be built for one of the back span. So the upper pylon has to withstand those unbalanced loads. Okay, and so, sorry. Sorry, we have some problems. Okay, so like that. Okay, now it's working. Okay. So this one. Okay, so regarding the PT, we have several families. First one was the temporary PT that were mainly PT bars that were used to launch the front traveler and the segments. without the presence of the PT cables, and the rest are PT cables that some of them are temporary and others are permanent. This situation is due to the compression and tension that are taken by the main by the top of the bottom slab, and has to be fine-tuned during the construction sequence. Okay, so for the in order to balance that weight between the main and the back span, you can check here the requirement of the counterweight on the back span. Okay, the distance between stay cables in the main span is typically 12 meters, so 2 segments. And in the back span, we have 1 by each segment, so 7.50 meters. You also can check here that we have a monolithic connection in S2 in the anchor piers, in the immediate piers, which initially in our previous design we have there bearings, so we have to rearrange the global behavior of the bridge to accommodate what later we will explain about seismic spatial variability and also shaking. Okay. Also, you can check here that we have the steel internal frames, the delta frames, that are taking loads from the stay cable and pushing them to the post girder. For the main span, we have 2 different segments, one with a stay cable and others with normal stay cables, but the presence of the steel internal frame is required. Also, the width of the webs and the bottom slab and the top slab are fine-tuned, as Javier mentioned, minimum 0.30. Okay, and it has to be mentioned also that no transversal PT was used in the whole project, in the main bridge. Okay, so the first situation without the presence of stay cables is what you can check here. Okay, so in the back span, the main span, we have about 40 meters of free span length. Okay. It's worth mentioning that you can check in phase 11, we have the front travelers launch, and the weight of the front traveler was very similar to the weight of a segment. It's about 2,400 kilonewtons. Okay, so this one. Sorry. I don't know. Well, one of the slides has gone wrong, but I will explain. It's what's about the pylon and the displacement expected during the construction. The pylon maximum displacement in the longitudinal direction was about 1.2 meters. Okay, and in the main span and the back span, the displacement of the deck was also good. So with this, one thing that has to be taken into account is that the gap of the stay cable bundle in the forward tube, so as not to touch in any of the sides, which was really demanding. So okay. For these elements, which require very complex geometry for the reinforcement, okay, in the shoes. Some of them were done, like you can check here, with precast shoes that later were lifted to the deck and set into position. You can check here also, okay, and it's worth also mentioning as well. It's worth mentioning that in the left, you can check that, of course, these elements, in order to transfer the load, require those shear stud and those plate that interrupts the transversal reinforcement. Okay, so a different rearrangement of the transversal reinforcement in each of the segments has to be done so as to being able to transmit the transversal forces. And remember that we don't have any transversal PT. Okay, as well. Okay, pier table, T1 and T2 towers. Of course, during design, it was studied by solid finite element analysis. Okay, but also during construction, it was required to study the different stages of construction. Okay, so that we were able to withstand all the loads. Okay. So here you have step by step, just some of the steps that were taken into account, so that we could make it possible. Also, you will see later that there was a uplift platform from where we got to uplift the from tower that has to be embedded in this complex geometry. Okay. So you can check here some photos of the lift element, the umbrella, and the so-called umbrella, and the front shower, and some of the diaphragms of the second phase of the pier table. So, okay, another feature that we were mentioning is the tie downs in S2 and S3. Okay, so you have here the different scenarios that different construction sequence that we have to go through. And the maximum free cantilever with the stake cables is the one that you have there. So more than 100 meters in the main span and about 90 meters in the back. And we require for this element from alliance with the construction team that in order not to be not to stop the works of construction, it was required to get out of the solution with a temporary construction. That is the one that you have there. Due to the complex geometry, reinforcement, and also all the PT cables that those piers were going to have. So mainly the bending moments coming from the global analysis were taken by the tension and compression of those legs. And you have here the pictures of some of them. You can also check that it was very tight, very complex. We have a lot of reinforcement. All the anchor PT bars have to be fine-tuned, each of them of one length, so that everything fits into this tight area. It was required to go in different stages, so we required not to interrupt the underslam from traveler. Okay. And also from the construction sequence, we were required to withstand the seismic event during construction. Typically, in this situation, we were about 4 seconds. Okay, and at the right, you have the tension compression that we're taking by each of the legs, and also in the last one, you can check that we carried out a situation where a plastic hinge was allowed on those structures. So, all the construction phases were studied, okay, and different periods for the sickness event. So you can check here that the analysis carried out to get and fine tune those elements so that at the maximum compression rotation we were taking with a nonlinear analysis geometrically and material non-linearity to get to those plastic hinge. Okay. So this one pier table is 1 and 4, already mentioned by Javier. The main goal for this is that we have some uplift forces on the backspan pier, and the goal was to be able to come up with a solution that the bearing were always on compression. Okay, it's very, very tight and complex to build, but it works pretty well. Of course, period table was studied during the design, but also during the construction phase in order to accommodate all the construction joints. Another feature was mentioned main span closure. It was pretty easy to play with the main span. Okay, with 500 kilonewtons, we were able to place to make a clip of 100 millimeters. So it was pretty easy. Also, all the elements have to be designed to withstand the construction loads. Some of the rail beams that were also used in the back span pier closure were used in the main span. Here you have a sketch of the situation. Okay, and finally, okay, those are just some real photos of the bridge, no renders. So we ended up happy. Okay. Now, Pedro, my colleague Pedro.
Well, thank you, Jose Manuel. I will talk a little bit about the special studies we have performed on this project. They are not usual to do in ordinary bridge, ordinary situation, but we had to, we were forced to do them because they were essential and effective laws and governing laws actually. So mainly this condition were poor soil condition, as Javier mentioned earlier, high traffic of vessels, ships, bulk carriers, oil tankers, and we expect the COE study shows that we have about 110 meganewtons on each pier of the on each foundation of the towers. The region is highly seismic, and well, I will speak about the spatial variability briefly. Above all that, we also have seasonal typhoons and extreme wind situation. As you can see this in this view, between the two main foundations, two towers, the soil is very different. The soil is actually very loose. We have a large layer of silt. We have the bathymetry studies show a deep layer of, to be considered for scar, and then generally we are dealing with a very loose soil. This was different from what we knew from the initial studies, so we had to investigate how much displacement we need or what we should expect from this. So this is a finite element model of the soil structure interaction. Of course, this is shorter than what it is now. The piles are much deeper. And well, what you can see in this view is that the soil shows an accurate model of soil has been developed, and you can see the classification of soil in such large displacement. In further levels of the study, we modeled this with PY curves, a nonlinear curve to show to consider the nonlinearity of the soil layers, and this has been very essential part of the model. In case of vessel collision, in the left side you can see the ship impact, and well, but this is not always because of the seabed shape. There's a slope. The T2, one of the foundations, would show rotation, and the other on the right side you can see the one of our smaller piers which had stiffer soil and nothing on the top, which is a very critical condition, which caused plastification, and this had to be avoided. A detailed model of the foundation under vessel collision. You can see the actual force flow. This helped us to design the reinforcement in a very efficient way. You can see the cut from this part and the tension due to vessel collision. Again, you can see a very detailed finite element model on the left side, and the stress level on the ultimate limit state, and actually beyond that. So we have the nonlinear material, and above this nonlinearity of the parts, we managed to design a casing around the parts for, I believe, 5 meters length. So in case of the vessel collision, this absorbs the energy, and all of this together allowed us to have a much smaller overall foundation, as otherwise we had to be using more material. And now I will talk a little bit about the seismicity of the region. The Philippines is highly seismic, and you can see on the right side the faults around the site. It is a very active region. As Javier mentioned, we have about 0.4, 0.5 G of acceleration, ground acceleration in one of our soils. And to give you an understanding of how it behaves, I'm showing the first vibration mode briefly. I have 3 minutes. Okay. Well, one of the studies we have done is a pushover analysis, which tells us the capacity of structure against the earthquake loading. You can see the earthquake, the piers actually of the bridge has a lot of capacity. That's because the governing load in this case is the wind. Now I'll briefly talk about spatial variability. As Javier said, also we have 3 different soil, and in this combination of this effect with very high seismicity cause a phenomenon called spatial variability of ground motion, which means between point 1 and 2, A or B, you don't have essentially the same motion. This is a very special case. And one of the things that affect this is the local soil, which amplifies the motion. So as you can see, we have the this is called conditional simulation of motions, which we take one of the motions, very similar to one. In this case, Gigi, Iwate, and Darfield. And then what we do is we simulate according to that the site. We simulate the motions, and you can obviously see the delay, at least in this case, and the motions are similar but not the same. As a result, this is not playing. Okay, this is similar to the previous video. It's not playing. I don't know why, but it will show the movement of the bridge. Oh, it's going. Yeah. So what we can expect from this one is the motion at this pier is not necessarily similar to the last one, and that caused extra forces in the bridge. Okay. Eurocode, we have also used Eurocode approach, which is one of the only norms that give you an approach to calculate this. This gives us about 25 centimeters of displacement between them. This is a comparison between the forces, And as also he said, okay, very good. It was mentioned before, this force was one of the effects for to cause this to result in this shape of geometry. I have one more topic. I will have to squeeze this. We have done a wind tunnel test, very detailed wind tunnel test, elaborated model were generated. But one thing I wanted to talk about is the effect, the CFD, computational fluid dynamics, that we have used. We have used prior to do the wind tunnels. We did this to optimize the shape. It was very effective. I will skip this part. This will talk about the cross, as Robert mentioned, and how we optimize this to reduce the drag. See the big wake here, and how much it affects the shape. I'll finalize my my talk with this video, which it shows the vortice shedding, and in this great 250 kilometers per hour wind speed. And thank you. Yeah. Next is Acciona.
Thank you. Thank you, Pedram. I think you have to stop sharing so that yeah. Thank you, Pedram.
No. There you go.
Hello. So now we are going to share the, no, we are going to present the construction features. It will be Antonio Jane, Javier Fernandez from Rubrica, and myself, Antonio Jane, and myself from Acciona. Okay, I think it's, you see the screen? Yes.
Yes.
Okay, so now it's time for detailing the main construction topics. Emphasis will be shown. Sorry, can you hear me? Emphasis will be shown to the innovative decisions made all along the Cebu main bridge construction journey. The main topics that we want to highlight are the logistics in terms of concrete fabrication, transport and placement. The use of offshore technology was imperative as it was built mainly above water. And journey started by foundations, continued by piers, bottom pylon, pier tables, pylon mast, ornamental cross, and the deck. Some hints will be given to the strategic smart tools at hand during the whole process to rule the deck geometry control. Some time will be dedicated to Rubrica from Traveler and its main innovative benefits through the whole deck construction process. The main bridge construction, in red you see there, was assisted by three main yards. The SRP, where the batching plants were located. All the concrete was loaded into trucks and driven up to the next facility, which was the CPA, which was a small yard where we were pre-assembling reinforcement cages for piles and mainly for piers, and precasting some precast elements from the bridge, such as the precast panels on the pile caps and the pier, the foots from the deck. You will see that later. And the site offices were there because it was to the proximity. It was very close to the project. So and then next from there, all was barged into jetties and it was transported into temporary causeway, the bridge itself, so precast yard, or the whole project permanent causeway and other bridges. Two tower cranes of 40 tons with a height of around 160 meters high were well braced to the pylon shafts and founded at both pylons pile caps. So here you see the SRP yard with the main offices, employers, and the construction joint venture offices, and the batching plants. The batching plants were had a capacity of 2,000 cubic meters per day, and total concrete in the bridge was around the 30% of the total concrete volume on the whole project, and it was mainly 70% of the in substructure, including foundations, and 30% in the deck. Mix design was key, and it was thoroughly analyzed in order to meet durability requirements with a maximum content in fly ashes up to a 30% in order to increase as much as possible the non-penetration of ion chlor. And different techniques of concrete logistics were used for the different elements and different mixes. Here you can see the CPA yard, and I go fast. So the pile rebar cages you see there, and briefly, the rebar cages for the piles were done very with on tolerance with couplers and templates. Think about that these they were having a size, 2,500 millimeters diameter of a king bed size, and they were having 2 layers of bundles of 2 diameter of 50 millimeters diameter bars. All was coupled, no splices were there. And there were up to a maximum of per splice with couplers, position couplers, 96 couplers to be done. So they were all done on the yard, except only one on. We will see that later with on the site on the casings. Worth mentioning those 2 references. The precast panels as for the soffit of the pile caps were produced here, so you can see some pictures of the rebar, the works. Nothing. I mean, what was special is the way they were installed. And what was special and innovative is that we were executing piles, and we will see that later. At the same time that we were placing precast panels. We'll see that later. 60 total precast slabs were produced, and here you see day and night CPA working. For the onshore foundations, we just have 2, and they were done on a reclamated area near the Shell Island with normal equipment. So it was a 1 rig for 2 foundations, and so you can see here pictures. For the offshore foundations, we were having 4 of them, so S1, S2 pylon and both pylons. We had 3 from work teams, so 3 drilling spud barges, and with 3 drilling, 3 rigs to perform 4 foundations. So barges were. The piles were executed in retreat by rows, as you can see there. So barges were positioned once for the installation of 1 row of 5 piles, as you can see in red. So the stages and briefly, barge positioning, GPS, casing positioning, casing installation. The tolerances were chosen internally to be smaller than what the guidelines were requiring because there were a lot of rebars, and we will see that later. Drilling and polymers were necessary, and then installation of rebar cages. Worth to mention that those rebar cages, they were up to 100 tons. Only 1 splice was done on top of the pile with the 96 couplers, as we have said there, and we were using tilting tables in order to minimize as much as possible the deflections of the rebar cages. Then you can see there the picture, installing the rebar cage, and finally the pouring. Worth mention, the mix was very well studied for heating control during curing phase. Concrete was fabricated in the batching plants from SRP, as we have said, then transported into the CPA and boarded. The strategy and logistic, was key, as you can imagine, for the design of the mix in terms of workability. So with 8-hour retentions, specifically for the piles. As a comparative, between offshore and onshore pile construction, there was 2-3 piles per week for the offshore, whilst onshore it was 5 to 6. Now, Antonio, if
Thank you, Laura.
Continue.
To continue with the offshore foundations, the prefabricated precast panels were shifted to each one of the pile caps and installed. The purpose of this was basically to act as a temporary soffit formwork in order to execute the rebar and concreting works of the pile cap. To install these precast special gadget was used, it was grouted, and once it was grouted, the stitch joints between the different precast were concreted, the formwork in the perimeter of this precast was installed, and the rebar works were able to start. The offshore pile caps were divided into two different phases. One phase consisted on pouring an initial 1 meter height on top of these precast slabs. The second phase was the remaining 4.5 meter height on the pile caps. And for this, there was a total of approximately 450 tons in this first phase. There were different rebar mitigation measures that had already been implemented or incorporated in the working shop drawings. There were T-heads on the edges of the piles in order to avoid the big lap length and congestion of rebar. And another mitigation measure that was taken for this first phase was to remove the pylon starter bars from this first phase in order to minimize any possible rebar congestion and make sure that on the consequent stage, the pylon starter bars were going to be positioned properly. After execution of the first pour that we saw in the previous picture, it was approximately 800 cubic meter. It lasted around 18 hours. The treatment of the construction joint was prepared and gave pace for the second phase rebar works. In the second phase, there were around 250 tons of rebar, and approximately for the second phase, 3,000 cubic meters were poured in a period of 60 hours. This concreting was one of the most challenging and critical in the project, not only because of the quantity of concrete, but because of the logistics that were involved for shifting all the concrete barges in the canal, the personnel, and also the different coordination that was happening with the Cebu port authorities. For the concreting of this pile cap, a special design was prepared with the durability requirements to have proper temperature control, and there were two different mixes implemented with different workabilities depending on the phase that the concrete was happening.
Okay, for the piers, standard jumping form construction with pre-assembly rebar cages were used. Jumping forms of 5 meter segments were done. The cycle was 7 days. This was a standard that was used for the up to the soffit of the S1 and S4 piers, the S2 and S3 shafts up to the we will see that later, no, at the up to the diaphragm deck diaphragm soffit, and for the pylon, for the bottom pylon and the first 15 meters of the top pylon. You can see here how the rebar cages assembly that was key in order to win time, ensure safety, and avoid errors. What was key as well is the concrete mix was always looking for the necessary workability within the chosen construction logistics, as we have tried to explain at the very beginning, and always targeting durability requirements. You can see there a view of the rebar cages. Pier table, we are going to do it briefly. This edge pier, as Jose Manuel has explained, they restrain the deck transversally and vertically. And what was key here is that the bearings were replaceable. They were quite challenging to be installed on tolerance, but they were always working in compression. You can see as well, it was a pier table of 16 meters by 27 meters wide, and it has a strange shape, which was very difficult to be built. We did a very good job coordinating with design and construction, so that this was built in 6 stages and trying to meet as much as trying to meet the tolerances. Here you see the bearings. I'm not going to detail too much. That was described by CFC. An independent shoring system was implemented, 50 meters high temporary props, which were supporting the ULMA scaffolding, and which was prepared for the 6 stages of the pour. And there were jacks for the pouring stages to be transferring the load to the permanent bearings, because they were installed at the same time as we were pouring, the clamp of the pier head and the clamp of the pier table. And what was very innovative, and this is important through all the presentation, is that this was as well a tool that allowed to adjust the deck before the back span closure. You have there the sketch. No, by means of the temporary props and jacks, it was possible to rotate that pier table and to adjust to the desired geometry. For the pylon pier table, briefly, what was key for construction and innovative was to maintain the schedule and to try to avoid the waste of times, and at the same time that the pylon shaft was being built, the two form travelers were joined together and they were assembled on top of the pylon pile caps. Then there was this special structure that Rubrica will discuss, this umbrella that was the support of 4 heavy lifting jacks in order to lift up those form travelers. And what was innovative is that we were using, in order to build the pier tables, the same equipment that was going to be the key and the tool to build the deck. Next slide, you see the pier table stages, so bottom slab, the webs and the diaphragm second stage, and the top slab, and then between the webs and then the cantilever top slab. Here you have the big amount that Jose Manuel was showing of rebars and PT, and some pictures on the process. Here you have a final bird view, which a very nice view of the pylon pier table fully poured, which I like a lot this picture. Go on, Antonio.
Yeah. Okay. I want to highlight for the next phases we will discuss the construction of the deck and the top pylon. They were carried out during COVID-19 pandemic, so special measures were taken to divide the teams into different working locations, accommodations, in order to minimize the exposure on the activities that were done on site. So all this happened during 2020-2021. So for the top of the pylon, this represented a new challenge in the project. The main goal was to reach the upper pylon as fast as possible in order to be able to start with the anchor box installation and for the stakeable activities, and with the iconic ornamental cross. The top pylon had a total of 21 pours, from where the first 10, the middle pylon, were executed using the same procedure as the lower pylon. So prefabrication of rebar cages was done. The ULMA self-climbing hydraulic formwork was utilized, and the pouring was carried out. I like this picture because this picture is showing the actual and daily situation of works on the site, where big container ships were constantly crossing the channel, passenger ships, and it required a very big coordination, not only for movement of personnel, but also during the concreting works and logistically. Next one, Laura. Okay, after completion of this middle pylon, the remaining 11 lifts on the upper pylon had 2 further complications. One was the correct installation of 14 number of anchor boxes, and the other one was the installation of 40-meter height ornamental cross in 4 sides of the pylon. For the installation of the first anchor box, a temporary or a permanent steel frame was installed in order to make sure that the position of the anchor box was the correct one. Here we see some pictures of the ornamental cross. different procedures. And an average of approximately 1 week per lift was able to be achieved on the upper pylon. And the normal sequence of works were already shown before, but we will move with the ornamental cross. The ornamental cross was, as mentioned before, 40-meter height. It was placed in 4 phases. On the top of the cross, there was a horizontal portion of 6-meter wide. The cross was of stainless steel, and there was no visible anchorage on the outer part of the cross after the completion of the works. We see some pictures here of the process of installation of this ornamental cross, where the anchors were embedded inside of the pylon during the execution works. After the installation of this ornamental cross, on the edges of this cross, we were installing all the LED lights that Robert had mentioned before. So the deck construction was in situ concrete. In the main span, there were segments of 6 meters. The back span, there were segments of 7.15. And there was basically a construction of free cantilever method during the first segments, which basically allow and gave flexibility for being able to adjust the parameters in the geometric control of execution of the deck. The process of the construction was complex due to the unbalanced situation that has been mentioned before. There were 2 segments on the main span being constructed, while only 1 was being executed on the back span. In order to be able to optimize this cycle, there were different innovative techniques and required coordination, not only with a designer, but also with a form traveler manufacturer, Rubrica, that we'll discuss later. One of these optimization was to delay the execution of the inner counterweight as far back in the process as possible. The construction of the segment was done in 1 full monolithic pour or 1 phase, so concreting the bottom, the web, and the top deck slab all at one time. For being able to execute this, we needed a proper concrete mix design to be able to have the workability and the timing, retention times required for doing this. And also, it was a key to have early strength in the concrete in order to be able to strip the inner formwork as soon as possible, and also proceed with the stressing of the PT bars and the stay cables. Another optimization was the launching of the form traveler to the next segment prior to erection of the stays, and the counterweights became or were taken out of this critical path as they were prepared in advance by inserts on the deck in order to be able to pour them on a later phase. After reaching there was also a prefabrication of the delta frames, as had been already mentioned before. This was speeding up all the cycle of the execution of the segments. And another thing that is good to mention was, after reaching the 6th segment on the main span and on the back span, additional auxiliary means were lifted onto top of the deck, such as mobile cranes, boom trucks, and spider concreting pumps, in order to be able to continue with the cycle of the deck. And here we see a typical cycle of the execution, which was a stressing of the PT bars, launching of the traveler that will be discussed now, execution of the rebars, and then concreting. Once it was concrete, the stay cable was installed. The installation of the stay cable was a standard procedure, so it was lifting the duct together with the master strand and the second strand, threading the master strand on the top anchorage, threading on the bottom anchorage and stressing the master strand with a isotension jack. Afterwards, the threading continued using the shuttle system by the winch pulling and lowering.
As it was mentioned by CFC before, one of the main keys of the design and the construction was to non-stop, and we as a team work a lot on this side to non-stop the deck, the standard deck cycle, because we had to do this connection between S2, S3 and the deck. So how was that done? It was done in preparation. So very first stage was done as a temporary structure, preparing for the last monolithical connection. So you can see there, we have the fifth stay at the back span stressed. We have the form traveler here on top of the pier, and the temporary connection has to be done at the stage of when the stay at the back span number 8 is stressed, and the monolithical connection has to be done when the stay 11 at the back span has to be done. So between those two and between those two, we have three full cycles to be preparing the final monolithical connection. And that was innovative, is to have a design and a construction procedure that was allowing us to not stop. And again, the same idea, and that was allowing us to adjust the deck geometry. So when we were doing this temporary structure, and we'll say that later, we were pulling down the deck towards the pier, and we were doing a geometry adjustment of the deck. Here you see the form traveler is on top, is the same as the picture, is on top of the pier head, but the pier head is not yet finalized because we need to leave the space proofing for the form traveler to pass. So here you see there is 1.5 meters between the top starter bars and the soffit of the form traveler. We are working for this future monolithical connection. We are allocating couplers on the deck, on the webs, together with Rubrica and CFC. That was coordinated. How was those phases could be done. So imagine that nice work. And then we should allocate some on the design as well, some holes or windows without any rebar to pass through that future PT that CFC was explaining for the monolithic connection. Here you see briefly, because it has a lot of stages, but briefly, once the segment on top of the pier was done, so we were working on segments 9, 10, and 11 on the back span, we were preparing for that temporary connection and the future monolithic. So the pier heads could start going up, the formworks, and then the diaphragm, that green part, this first stage diaphragm, could be, you remember those couplers, although that the rebar execution of those works was done for the monolithic connection as well, and rebar and PT. Okay, and the bottom part of that blue part is where the anchorages of those pulling PT bars are located. So that's the anchorage. Then we will continue. We were continuing with the installation element by element of this structural steel blocking structure that Jose Manuel was showing, with lots of anchoring bars. You see them here, on the top here on the diaphragm, and here hanging, because all this deck had to be pulled down and go down. It went down 200 millimeters, but we were prepared for more, 350. So we were always having plans Bs and Cs and Ds. And here we are installing the top jacks to pull down the deck at when needed, when this when it was required, and then we pull it down 200 millimeters. Then we could pour this concrete so that we anchor all those bars that were for this temporary structure. Then we turn out of the nut, and the temporary structure was ready. Then then remember that we have 3 full cycles, 30 other days to just prepare for this rebar, continuing with the vertical PT and pour. to be ready for the monolithical structure. And we never stopped the cycle, so that was key. We as a team, we asked for that, and we had it, and it was very good work. So monolithic connection was ready. You see here some pictures, July 2021 with the next state 12B, November 2021 with the back span closure already done, and then we could continue with the deck. Unfortunately, we don't have too much time to discuss about the closure, so you have here some pictures on the back span closure done with the form traveler from Rubrica and some steel beams to adjust the geometry again, the main span closure. And what I would like to mention is that we had a lot of jokers and alternative plans. It was a very smart design for a contractor requiring a lot of alternative, and we wanted to be ready for black swans, and we had black swans. So we had a good knowledge of the concrete mix, rip and shrinkage and modulus, the more the better. And we have shown the key stages where we could adjust the deck to meet the geometry. Okay, thank you. Now it's we are going to discuss about the Rubrica form traveler.
Thank you, Laura.
And I have to thank you.
Okay, I'm Javier Fernandez. I'm here in behalf of Rubrica. We here in this project, we design and supply the formwork problems and also the lifting structure. Okay. My presentation will be structured in 3 main points. What we did with the adaptation and assembly of the formwork problem, what is the standard cycle, and just like a conclusion of what we did unique for this bridge. In this picture, you can see on the left side, you can see the Mercy phone traveler that was actually adapted to the Cebu-Link of the CICLEX project. Main features here is to adapt the traveler to the seismic actions and also for the wind action, for the tropical actions. Okay, this was working together with CFC and Acciona in this case for lowering the weights and COGs to have back the reaction and the action that we need to consider. So the design of the traveler, the equipment was capable to resist the 50 years return period of the seismic event, and we consider the 30% we consider okay at the end of these combination functions. Standard calculation was considered for the lifting and working, but also for the accidental or extraordinary actions. Okay, the design wind was considered in 250 kilometers per hour. Okay, with the tropical storm. CFD analysis was performed. This is just internal for us, for Rubrica, just to confirm that the traveler itself was not affecting to the dry coefficient of the deck, and we didn't have or expect any additional loads coming from the geometry of the equipment. This is what we consider at the end is 225 kilometers per hour, but because of the height and also the speed up of the because of the deck geometry, we consider at the end a wind speed, a gust of 82 meters per second, which is here. These are the different stages we consider for the equipment. Everything was stated in the design basis as always. And this was our starting point for the design of the troll. What we did at the beginning is to propose a lifting structure to what internally we call an umbrella, okay, for allowing the construction site to perform the pier head together with the same equipment that they are going to build the main state bridge. The critical part here is the longitudinal slope. That is why there is a small offset between the center of the pile and the center of the positioning of the umbrella. And also this longitudinal slope was also considered for the installation of the umbrella. You can see two blue devices, which actually acts as centering devices and also bracing devices, okay, during the lift. Here is the final distribution of the umbrella, and you can see the strand jacks over there, which each of one has a capacity of 200 tons. This capacity actually was a limitation for us during the construction of the pier, the pool. How we perform the lifting? The lifting was quite of innovative, but we also applied this in many projects. We assembled both trouble at the bottom part, the top of the pile cap. We joined both in tails. This is special joints, usually pre-stressed. And we then installed the lifting structure on the top of the deck. In this case, the deck was monolithic to the pier, so part of the legs of the umbrella was embedded directly on the diaphragm on the deck. Special device was also used for the lifting. This is because we, as Laura said, we needed to consider plane A, B, C, and D. So some adjustment of the position of the travelers has been were considered. So we did actually include an adjustment up to 200 millimeters per point to be able to adapt the position of the foam traveler once we reach the upper position. Okay. Also, the blue element that we mentioned before was also capable to address the foam travelers to the correct alignment. The distribution of elements you see here, you can see at the table. Actually, as we understand that the pier head construction is a long time, it's a long process. Actually, we didn't. We always consider that the strand jack is not needed to be permanently on the umbrella. Okay, so our intention was always to use the strand jack for lifting, and once on the correct height, okay, remove or be able to remove the jack, okay, the strand jack, and just remain with the cables. Okay, that is the intention of this whole set of elements. Okay, here in the main. So there were designed some let's say some supports on the pile cap that was designed by Acciona, and also once everything was set, we move up all the system. The blue device that I mentioned before was actually a wind restraint action that acts in two ways. One is that raising the traveler to the top once it's at the correct height. Okay, so in transversal direction we can adjust a little bit the system, and also once the equipment is on the correct height, we are able to anchor it to this device and avoid or transmit directly to the pier the transversal action, okay, the wind action. This is the device that you can see there before doing the lifting. Okay, and once the traveler is on the correct height, this device was also capable to push with jacks, okay, to maintain the positioning while the tilting of the travelers for adapting the slope to the longitudinal bridge slope. I mentioned before about the limitation of the jack, of the strand jacks, actually of the strands, 200 tons, and this is because of that limitation we came to a solution to avoid the additional pieces of concrete, okay, loaded into the jacks and also into the umbrella. So this is the more or less the percentage of loads, okay, that are going to or should we're going to the umbrella. The worst scenario was always to consider the self weight of the umbrella itself, the weight of the travelers, and also the first pouring, which is the bottom slab. Okay, and all the remaining stages actually were released from the weight of the next stages were not transmitted directly to the umbrella, because we came up with a solution, okay, for a load at every stage all the anchors, okay, and reload again to the new position. So in this way, we were able to avoid the increment of concrete stages, okay, on the umbrella. About the typical cycle of the traveler, Antonio already explained a little bit, but mainly I'm going to focus in the three main points that it's on our side, which is the launching of the traveler, the positioning of the traveler, and also the inner part. Starting with the external part, the external part is composed by main C-frame that you can see in green over there, okay, and the main anchor that you can see in red with a blue lag, okay, that is the configuration of the traveler during working is anchored in the same alignment in transversal shape, but in longitudinal, okay, it's separated in the same length of the segment. Okay, this is for maintaining more or less the efforts and be consistent with the reaction and the designer, okay, of the concrete. But in green launching, we remove the load from the main anchors, and the reactions goes to a different way. Goes directly to the C-frame, which is the translation element at the end, and also goes to the underneath roller, which is on the bottom part of the deck. In this case, it's represented in. For launching the traveler, it is quite simple. It's hydraulically propelled, step by step. In this case, we use the same jack for launching the rails and for launching the traveler. It's just a matter of changing the support configuration. This is the jack that we use for launching the rails, and in this case, all the traveler is anchored in the full working situation. Okay, so the red anchors and the rear part is anchored, so we are able to push forward the deck directly using the same. Okay, once the rail is on position, in this case we don't anchor the rail, but it could be anchored. It depends on the type of the traveler, but in this case the deck was able to withstand all the loads along the path of the launching. So what we did actually is we remove all the load, we lower actually a little bit the traveler, and we remain all the load on the main rails. So the same jack that is pushing forward the rails are also pushing forward the traveler itself by means of rods. Once the traveler is on its position, actually main anchor is placed but not per stress. So we are, as the center of gravity of the whole system is on the front, we are able to, with the rear jack, we are able to tilt the front part, and we are able to adjust the plickup. Okay, the rear jack is hydraulic also, so everything is done hydraulic. In this case, the system after the precamber is set. Okay, it could be operated simultaneously both sides or just one side, as mentioned, just to adapt the structure. And also from the top part, there is also transversal adjustment. Usually, it's not needed because when you lift the traveler, the same overlap aligned the traveler, but sometimes it's required because of some adjustment overall in, for example, in the curve alignment that was mentioned. Okay. Once the tilting is performed and the precamber is set, then we place the rear anchors on the front anchors. The rear anchors actually are not receiving pulling load. It's just a matter of maintenance, the permanent contact between the rear part. Okay, the uplift forces. We need to assure that always it is a contact between the concrete and the structure. And the main anchor are the one actually receiving all the loads, okay, from the. In the other side, in the inner form, actually we are quite happy with this inner form. It is a little bit complex to use, but it's quite easy to operate. And in terms of load, actually when it starts to pull, they start to put the bottom slab, then they go to the webs, and when they arrive to the top slab, our design are going, or it is designed for transmitting all the loads from the top slab to the external part. So that, in terms of designing, do not increase.
1 minute, Javier.
Okay.
Sorry.
Do not increase the loads or any reinforcements on the deck. So there are two types of this is opening of the inner form. This is performing in our workshop. The inner form is set also for being folded and for adapting to different web thickness. And I have this is the reactions for launching. There's the only reaction that we transmit to the web. And I have a quick video of the operating of the trials in our workshop. Okay, this is the assembly of the opening already open, and you can see that this is already folded, the up and down movement for avoiding the delta frame, and also the ribs, and also the launching system that you can see. Okay, it's quite. I mean, it's a very complex element. In this case, the web was very tight, so the angle was a little bit complex for us. But this is what we do. So finally, what we did. Especially for this project, the lifting structure, the inner form, to accommodate the values of the hurricanes and seismic actions, and also for the curve alignment quickly, just to see how the deck is adapted. So we came up with an exterior part, okay, a telescopic part, okay, for adaptation of the web and also for the wings, okay, also for the wing. And that's it. So maybe Laura or I don't know, Daniel.
Yeah, I am showing.
So hello, good morning, everyone. So as you have noticed in the previous presentations by my colleagues, this project was full of technical challenges, but also other threats were present, and I would like to talk about those. Next, please. Although by the time our project started, Acciona had another project from our water business division that we may not deny that helped to the implementation. I would like to highlight that other factors, such as a good selection of our local partners, first Balfour and the NCI, engagement of local stakeholders in the critical activities, or an agile mobilization supported by our in-house 100 days plan, and a proper knowledge transfer within the company, like keeping as many staff as possible from the tender stage, or the involvement of our special business unit of road and bridges, specialized in this kind of complex projects, contributed to an effective launching of the project. Although Cebu is the second largest city in Philippines, it was not ready to supply the skilled manpower required for this kind of bridge. At the same time, the insular location made it difficult to attract people from other locations. The same problem we face for specialized subcontractors, and this required a high level of self-performance that exceeded the 80% of the works. Among others, execution of structures, precast yards, earthworks, or pavements. But self-performing alone by itself didn't resolve the issue. You still need a lot of labor, and more than 2,000 workers were required to erect this project. This required to diversify our manpower suppliers, and also with training and proper supervision, we overcame the initial lack of skill. We also foster loyalty and career development of some of the locals that actually, as of today, are working with us in other projects in Philippines. Next, please. The insular environment in itself is a big challenge for the supply chains, as you can imagine. And on top of it, the project suffered the container crisis that was one of the consequences of the pandemic. The problem was not only the extremely high prices, but also the lack of transportation at all. South Asia, because the strict measures that the Asian countries against COVID, and transportation was often delayed. Bear in mind that a big portion of the supplies in Philippines comes from Southeast Asia, and these ports are also usual stops in the transoceanic roads. How we did handle this? So we went to local as much as practical. We diversify our suppliers, and at design stage, we had the opportunity to look for more sustainable solutions that were adapted to the local capabilities and availability of materials. For example, we did this by designing an innovative slope protection of the causeway that allow us to be more flexible in the materials that we place at the core of it. Next, please. COVID restrictions were present in Philippines much longer than in other countries. Health services are not very well developed in Philippines, and the government opted for closing boundaries and applying a lot of restrictions to protect their people. This was a problem because sometimes our expats were out of the country when the boundaries were closed. On the other hand, the situation sometimes required to be stricter than the government restrictions, and we developed our own protocols that in the long term demonstrated to have been very effective, not only protecting our workers, but also containing the spread of the virus and improving the productivity. Actually, our construction joint venture was the first company in Philippines to be awarded by the Department of Labor and Deployment with the safety seal, COVID seal, as you can see in the picture. Yes, please. In December 2021, Cebu was hit by Typhoon Odette. That was the second strongest typhoon recorded in Philippines after Typhoon Yolanda in 2013. Winds of 280 kilometers per hour were recorded, and more than 400 casualties and $1 billion of US dollars in damages. Fortunately, we had closed the bridge only 2 months before, in October, and no significant damages in the permanent works happened. However, at the right bottom pictures, you can see the condition of our premises after the typhoon. They were fully destroyed. There is not a lot you can do in advance to deal with these black swans, but they were very hard days, working day and night without the basic needs, without electricity and water. And at the same time, people had to take care of their families and arrange for their personal lives. But thanks to the reaction and commitment of the team, that was outstanding. Only a few days later, we had new offices and resumed our operations. Yes, please. Then, after the Typhoon Odette, we still had another big challenge. At the moment, our program was targeting to finish the project around July 2022. But presidential elections were happening in May. So you can imagine what was the request. Yes, our client requested us to open to traffic by the end of April. So our first answer was no way. There was no way to do this. Imagine, we were still recovering from the typhoon and ramping up our activities. But by making the effort to understand each other, to understand the client's need, and the client also understood our constraints, we found and agreed a compromise solution to open the road to traffic safely and fully operational. And as you can see in the picture, we got it. And President Duterte was crossing the bridge on April 27, 2022. And finally, next slide, please. I just would like to conclude summarizing what I believe are the key factors for the success, despite all the technical and non-technical challenges that we have been sharing with you along this webinar. First is the excellent team in both the design and the execution of the works. Also, the excellent teams in the supervision, in the engineer side. This is not only providing the capability and skills to resolve the issue, but also made easier the communication and the achievement of the solutions and kept things moving. That was a priority given the tight schedule that we needed to fulfill. Of course, the commitment of the team, as I have said, with the targets of the project. This is especially important when challenge after challenge, and this project faced it a lot, the resilience of the people is tested. To have all kind of alternative plan, it has been also mentioned by several panelists, since as the complexity of the project increases, things tend to go different than expected, especially in a country like Philippines with its singularities, as we have been discussing. And finally, the most important, in my opinion, is the team building. I believe that today our panelists were a good representation of the top-notch professionals that have participated in this project from several roles and positions, and how we have worked together for a common goal and the success of this project. And this is all from my side. Thank you.
Okay, so thank you, Daniel. I'd like to thank all speakers today for this extremely interesting webinar, for the presentation. It's true that I'm very impressed with this project. And I apologize to Javier Fernandez from Rubrica for not introducing him at the beginning of the webinar. There were so many panelists and I skipped his name without realizing. Sorry, Javier. I'm afraid we have we have only time for a couple of questions. I discovered that most of the panelists are rebels because they have been answering the question during the presentation. So now I'm not pretty sure what to do. So I'm going to select a couple of questions not answered. And I will read loudly a couple of questions answered. So perhaps, I don't know, sorry because we have more than almost 40 questions in the Q&A box. So perhaps, I don't know, One question, what response reduction factor for pylon has been adopted for seismic design? Perhaps this is addressed to Javier Muñoz, I don't know. Javier?
Yeah, we actually did not take into account any reduction factor, any seismic factor. Since we carried out pushover analysis, we evaluated with this analysis what was the actual capacity. So from a practical point of view, correct me if I'm wrong, Pedram, I think what we reached was about less than 1.5, no? I think it was 1.2, 1.2. But we based our analysis on the pushover and with a given reinforcement, targeting an elastic design, actually. We were not counting on this, let's say, ductility behavior, yeah. Because it was all connected to the ship impact and the wind. Because even though we could optimize the design in the seismic situation, later the wind requires more reinforcement and even the ship impact. So at the end, it was kind of balanced between all these load cases.
Okay, thank you, Javier. And this is addressed to Laura. For what force you designed the head section, maximum pounding of deck to pier section?
Yeah, it was help me, Jose Manuel, because I think it was 4 bars of 4 PT bars of 50 millimeters diameter, and it was a maximum of it was 100 tons was for this 200 millimeters pull down. This is the question, right? So having to account that it was 4 bars of 50 millimeters, I will answer that later on. I'm looking at it. I don't have it in my memory. Sorry for that. But it's 4 bars of 50 millimeters section.
Okay, thank you, Laura. Another question, seismic resistant for such vital bridge, are any plastic hinges allowed? If yes, what are its locations? You know, perhaps, I don't know, again, Carlos Casado, I'm not sure.
Well, I can go again. No, there is not considered any plastic hinges in the design, or it's based on elastic design. It's a monolithic connections that you've seen in most of the connections substructure and superstructure, and we did not take into account any. Actually, this was a discussion with the independent checker, but we all agreed that we will follow this approach without any hinges in our design.
Okay, there are people asking where is the website where we upload the recording webinars. So Brinda, could you be so kind to upload it again in the chat? Because there are people who have been entering after the beginning. Okay, so what was the return period for seismic event? 470 years or 2040? 175 years. Yeah, what was the return period for seismic event? It's pretty clear. The question is between 475 years or 2,475 years. I don't.
I mean, it was based on 2 seismic conditions, let's say frequent earthquake and an extreme earthquake, and I think it was based on
disaster code
and
100 and 1,000 years.
Yeah,
that's true. 100 and 1,000.
Yeah.
Okay. Okay, perhaps the last question. What parameter do you consider in order to design the project by pushover? Perhaps it's for Pedro.
Yeah.
Well, I should talk on this screen. The pushover generally, well, you push it until you actually see how much the capacity it has. But the pushover curve corresponds to the displacement spectrum. So it's very simple to see for that spectrum and for the extra for the extra yielding, how much it is needed. So it's very interactive and very easy to understand figure.
Okay, so I'm not sure, Brenda, if we can have time for a couple of questions more, or we have to finish, because I'm not sure if.
Loli, just a quick one. It was 40 tons and capacity of 4 bars of 50
Okay.
millimeters. Okay. It
Okay.
was a matter of 200 millimeters pulling down.
Okay. So finally, I would like to thank the panelists for the generosity in sharing their knowledge for the outstanding project they have undertaken and for the effort in preparing this webinar. And to thank so many online attendees for the participation and interest in the webinar. And of course to IABSE for making possible and facilitating this type of event, which is having such good results. So have a nice rest of the week. And thank you so much to everybody. Bye.
Thank you.
Thank you.
Thank you.
Bye.
Yeah. Bye-bye.
Bye. I'm going to copy the questions.